I'm, I'm going to say once more that I'm very grateful to the organizers for inviting me to this advanced workshop at a remarkable place. Yes. And, oh, thank you. So, although I see now that the density of the population in the audience became a little bit smaller than it was yesterday or the day before yesterday, probably the result of the yesterday dinner. Yes? Okay. So, is there a laser pointer somewhere? Here it is. Yes? Okay, but you know, okay. I changed the subject compared to the initial one. I was going to talk about superfluidity of supersolids, but listening to other people at this workshop, I realized that there is quite a bit of interest to disordered quantum systems. And this is what I will do. Probably I have to. Yes, turn off Wi-Fi. View, full screen mode. View. Full screen mode here. Yes, okay. And then I decided to talk about new trends in the physics of disordered quantum systems with the focus on ultra-cold quantum gases. Here, I will tell you, of course, slightly later in my talk, what are these new trends. Here are my affiliations, which are usually very many, but I'm actually at LPTMS in Orsay, in France. When I'm outside of France, I'm saying that I'm from Paris, but here is Christophe Salomon in the first row, and he would definitely say that this is wrong, this is not true. Yes? So this is the outline of my talk, and the results that I will be presenting, they have been obtained in active collaboration with Luis Santos and Xiaolong Deng from the University of Hanover, then with Boris Altshuler from Columbia University in the US, and Vladimir Kravtsov from Trieste. So, now, first a short remark. Why do we study ultra-cold atoms in disorder? During, let's say, 30, 40 years, people studied a lot of dirty electron systems, and they obtained very nice results, and so on and so forth. Why to study ultra-cold atoms? This is an interesting question, and the initial goal was trivial. It was related to the so-called atom lasers. I think that everybody in this audience knows what is atom laser. You go to a shop, you buy an optical laser, then you come to your lab, you replace photons with neutral atoms, and this is an atom laser. Yes? This is at least a simplified view of theorists. Yes? So, then the idea was that making a narrow atom waveguide on a chip, one can direct a strongly correlated atomic beam, hopefully Bose-Einstein condensate. There was such a project of David Giriod-Lan, for example, on a surface and study its quality. Yes? But what people say that when you have an atom waveguide on a chip, the imperfections of a chip, they produce sort of disordered system for this coherent beam, which breaks the coherence. How this happens, one should study, and so on. And people started to study this type of systems. But rather quickly, it became clear that there are many more interesting questions in this physics, in particular, basic questions. And that's what I will talk about. So, you know, first of all, something which is very well known. People in the last rows, do you hear me very well? Good. what is well known is the so-called Anderson localization. Imagine, please, that you have many particle system in disorder. What are transport and localization properties? So this is the disorder potential within my drawing facilities, and these are my particles. Yes? And Anderson in 1958 came up with an idea that destructive interference in the scattering of a particle from random defects leads to the localization of the wave function. Yes? The wave function can be localized on a certain size, yes, which makes the conductivity for electrons 0. Let me mention at this point that Anderson localization by itself is a single particle phenomenon. I do not need many particles in the system to observe Anderson localization, yes. How the interaction between particles influences localization properties, it's a different question. Now I continue. So, people were studying disordered systems for several tens of years, and what is presently known is the so-called Anderson transition, the transition from localized to delocalized states, from zero conductivity to finite conductivity. And what is already found is Anderson localization of light, microwave, sound waves, electrons in solids. And usually I was saying recently, but now I should say 10 years ago, Anderson localization of neutral atoms. Yes. I would mention here that for non-interacting particles and short-range disorder, all single particle states in 1 dimension and 2 dimension are localized. Yes. This is quite remarkable. Imagine, please, that you have a disorder potential that small and the particle energy that big, much larger than the amplitude of the disorder. And the wave function is still localized on a finite size. It's only a matter of the localization length, the size on which the wave function is localized. And, you know, with this knowledge, people started to study cold atoms in disorder. And remarkable first experiments observing Anderson localization of cold atoms have been done in the group of Alain Aspect in Palazzo. Now he's in Palazzo, he was in Orsay. Yes. And in the group of Massimo Inguscio at LENS. Yes. I should probably mention here the group of Massimo Inguscio and Giovanni Modugno. Yes. And what now there is a large variety of experiments in various groups all over the world. I will not enter into detail. I only say that the first experiment was absolutely remarkable. It actually repeats the Nobel work of Eric Cornell, Carl Lyman, and Wolfgang Ketterle. To some extent repeats. Imagine that you have a trapping potential. This is green. And you put atoms which form Bose-Einstein condensate, yes? Then you superimpose a disorder potential, which, this is my disorder potential, which leads to density modulations. And the first experiment of Alain Aspect was in the quasi-one-dimensional geometry. People from condensed matter, if such people are present, do not be surprised when I say Bose-Einstein condensation in 1 dimension. It's a finite size effect. Yes, because the trapping potential introduces finite size. Then, there is a very simple question. Now switch off the trapping potential, but still keep the disorder. Yes? What happens? From the Nobel experiments of 1995, we know that if we switch trapping, the gas expands, and then the character of expansion tells you whether there is Bose-Einstein condensate or not. What happens here? What is the manifestation of the Anderson localization? And then, what they observed in the first work is that the expansion eventually stops. You get a leaving center of the cloud, but the tails of the density distribution are stationary. And they can be described by using, let's say, the localization theory of non-interacting particles. And that's what has been done Yes, and that's what it is. Absolutely remarkable experiment. And this stimulated the research in the domain of quantum gases and disorder. So, but then people started to have a look what happens, for example, for long-range interaction, yes, and so on. And then, as it usually happens, and people in condensed matter are usually saying that people who do quantum gases should look in the work in condensed matter and learn things. Yes, but I was also doing condensed matter in nuclear physics before, and what we know from literature is that there was a remarkable work of Levitov in 1997, where he says that if there is a regular lattice with on-site disorder and the hops of particle from lattice side to lattice side is unity divided by the distance in the power a, then if a larger than d means a larger than 3 in 3 dimensions, there is localization smaller than d, extended states, and when a is equal to d, then the states are critical. And this conclusion has been confirmed in a remarkable work of Alainer, Altshuler, Yefetov in 2011 for d equals 2. So that's what we know. We know that there is a critical hopping power or critical dimension, and we expect some interesting physics here. But now I wish to convey new messages on surprising transport properties. You know, if I were repeating the work of Levitov, then there is no reason to give a talk. So there will be something different. So now an important point comes. Hopping is just unity divided by r in the power a. That's it. No disorder in Levitov's work. So now I would like to say that during tens of years, people were saying that if the states are localized in disorder, they are localized. If they are extended, they are ergodic. Yes, and ergodic means that the special average is equivalent to the ensemble average. Yes, the only exception was the states in a single point of the mobility age in 3 dimensions. You know that in contrast to 1D and 2D, in 3 dimensions, there is Jaffe-Regel criterion, that particles with energies higher than a certain critical value are delocalized. And below, they are localized, single particle states. And then people were aware that the states at this singular point, the mobility edge, are not ergodic, they are multifractal. Yes? And this was it. But then fairly recently, for some mathematical models, for example, Berta lattice random matrix models, people found finite width bands of extended non-ergodic states. So what you have a band of non-ergodic states, then you have a band of ergodic states, and there is a border between them. And then this is a great interest, how the transition from non-ergodic extended to ergodic extended state happens. Yes, and then this was the work in 2015. Actually, the first one was Giulio Biroli in 2012, who only put his paper on the web and has withdrawn his paper from the journal because one of the famous Russian theoreticians was criticizing him very strongly. And he said, okay, now I withdraw the paper. I will not tell you the name of this theoretician, but it was not me. And it was not Altshuler, someone else. So it is interesting to see whether there are physical systems where we have bands of extended ergodic and extended non-ergodic states. And such systems exist, yes? And this was actually, this is the system of molecules in an optical lattice. You put molecules randomly, throw them to the optical lattice, they occupy lattice sides and do not tunnel. The lattice is deep. Then, what you do, and such an experiment is going on in Gila, in Colorado, for example. Then what you do, you transfer one of the molecules from the ground raw vibrational state to the excited J equal 1 raw vibrational state. This excitation can be transferred non-radiatively to here, to here, to here, to here, and so on. We have the so-called long-range Hopps-Levy flights, and the amplitude is the amplitude of hopping of the excitation from here to here, from here to here is unity divided by distance in the power of 3. An analogous system exists for nuclear spins, Rydberg atoms, NV centers, and diamonds, and so on. So it's a realistic system, and this is the system which we, in particular, were studying. This is the work of Luis Santos, Xiaolong Deng, Boris Altshuler, and myself, 2016. This is the problem with off-diagonal disorder. For theoreticians, this is the Hamiltonian, this is the hopping amplitude, and the excitation hops from side I to side J, and the hopping amplitude is unity divided by the distance of the power of 3. Yeah. And this term accounts for the anisotropy. This, again, for people who are interested in the influence of the interaction between particles on localization properties, they have to wait. This is a single particle problem in this form, so no interaction between the excitations. Imagine one excitation in the system. And then what one can do is exact diagonalization of this Hamiltonian, and for example, for 100 or even 1,000 realizations of the disorder. And this, what has been done in our work for the number of molecules, the number of these guys here, up to 80,000. It's a very long work, which allows us to extrapolate the number of particles tending to infinity. Then, so what one can do is to study the eigenstate properties. The interesting quantity is the ratio of the minimum to maximum level spacing. This is the spacing between levels n+1 and En, Rn. For localized state, one has the Poissonian distribution of R average, which is equal to 0.386, and for extended ergodic states, the Wigner-Dyson distribution, where this guy is equal to 0.53. One introduces the so-called moments. This is the wave function, number of particles, and this is something, yes. For extended ergodic state, this something is equal to Q minus 1. For localized states, it is 0. Then, people introduce the so-called fractal dimensions, dq, which is tau q divided by q minus 1. It is 0 for localized states, it is 1 for extended ergodic states, and then for extended non-ergodic states, it is between 0 and 1, yes? And it depends on q. You have a multifractal structure of the wave function. Then what people also do, they calculate the so-called spectrum of fractal dimensions. Skipping the details, otherwise I will have no time, I would say that it's called F over alpha. It's a fractal dimension of the set of those points R, where modulus psi squared is n in the power minus alpha. Sorry, this is alpha, not R. Yes? And then this spectrum is such that for extended ergodic states, this F over alpha is equal to 1 for alpha equal 1 and minus infinity for the other. For extended non-ergodic states, it has a parabolic form, and for localized states, it's a triangular form, yes? And this is how it scales with the number of particles in the system. This is a 10 equals infinity. So, what actually one can do is to study the eigenstates of the same of the Hamiltonian of this system. Yes, let's say excitation is transferred from here to here and so on. Yes, and then what has been found, what we expected, according to the work of Levitov and so on, that it is likely to be a critical state. And the answer is no. All states in 3 dimensions are extended. Yes? Then the energy scale is the filling factor, yes? And then in the center of the energy bands, extended states are ergodic, and in the outskirts they are extended non-ergodic. And the same dq, it's equal to 1 in the center, extended ergodic states, and then it drops. Yes? So there are only extended states in 3 dimensions. And what you see here is quite remarkable. You see that the fractal dimension dq, it has a cusp. The accuracy of the calculations does not allow us to conclude whether there is a jump and discontinuous behavior of d2, because the calculations are horribly complicated, but at least the cusp is present. Now, what does this all mean? What we are talking about is non-ergodic, ergodic transition at a given filling factor by varying the energy. Yes? So, why this is a phase transition? Why do I pronounce the word phase transition? As I already said, that D2 has at least a cusp at the border between ergodic and non-ergodic state. Then, let us do the following. Let us create an excitation in a given lattice site, yes, and look how it propagates in the system, yes. And for example, calculate the return probability P over T, T is time, that it is in the initial place, yes. And in the case of non-ergodic states, this P over T decays with increasing time much slower. So what you immediately see, once you get from ergodic to non-ergodic state, the return probability remains large. Yes? And I can also give you, I still have a few minutes at least, yes, a much more clear example. For example, one-dimensional quasi-crystal with power law hops. What very many people know is the so-called Aubry-Asbel-Harper model. You have a lattice, yes, and you put atoms in this lattice, yes. Then you superimpose a shallow incommensurate lattice with the amplitude delta. J is the hopping amplitude in this deep lattice, yes. And then it is very well known that for delta smaller than 2J, you have ergodic extended states, larger than 2J, localized states, either localized or extended ergodic. And this is only for nearest neighbor hopping, from here to here, from here to here. What happens if we have a power law hops, unity divided by R in the power A? Many interesting regimes in this system. And according to what I learned from several people, this type of system is close to what can be realized for trapped ions. Yes? This is the Hamiltonian. Now I put this J equal 1 and measure delta in the units of J. Yes? This is my hopping, and this is my superimposed incommensurate lattice. Skipping all details about interesting regimes which are present, what you see here that if this A is smaller than 1, yes, then all states, all eigenstates of the Hamiltonian are extended. But there are non-ergodic and ergodic states. This graph shows you the behavior of D2, the fractal dimension D2, inverse participation, related to the inverse participation ratio. Here, it is 1 extended ergodic states, but here at the border, it drops to 0.25 non-ergodic states. Yes? Right. So, therefore, it is quite interesting to compare with the case where A is 1.5 and there are localized states. Extended states, localized states. Fractal dimension drops to 0. Here it is significant. So here I pronounce the word phase transition. So look at this graph. Transition from extended ergodic to extended non-ergodic. Why? Because now let us do the excitation dynamic, localize the excitation in a certain site, and calculate P over T, the return probability at large times. It is T in the power of minus gamma at large times. And then this gamma, don't look at this graph, look at the blue one. And then gamma is close to 1 for extended ergodic states. Then it drops to 0.2 for extended non-ergodic states, so just sharp drop. So we clearly see a transition from extended ergodic to extended non-ergodic states. Yes, this is a very clear example. Yes, so I am close to the end. Yes. Here is conclusion, which says that Anderson localization still brings surprises. Before saying thank you for attention, I would like to say why. Because for more than 50 years, what we were thinking of is that in disordered quantum systems, there is only one disorder-related phase transition, Anderson transition from localized to extended states, from zero conductivity to finite conductivity. Now we see that it is very likely that there is one more transition, a transition from extended ergodic states to extended non-ergodic states, yes, which can be nicely studied with ultra-cold atoms, like in the system that they study at GLA, can be probably studied with trapped ions and so on. Why I am saying likely? Because what I actually showed you is the result of the solution of the single particle problem. How does the interaction between particles influence the character of non-ergodic extended state? How does it influence the transition from non-ergodic to ergodic state? We do not yet know. What we can do, and that's what I can do, to study the Anderson transition from localized to extended state. The technology is more or less known. One should work and so on, but how the transition from non-ergodic to ergodic state happens, it's not yet known, and people are working on that. So it is quite likely that after 50 years of studying disordered quantum system and Anderson transition, we grab one more phase transition in these systems. And now, I thank you for attention.
So thank you very much. Questions?